Good afternoon, everyone. This is Kama, and I welcome you to today's webinar that will be on Introduction to Fatigue Analysis of Elastomers using EPISAFE. This is today's overview. We will start with an introduction of EPISAFE for elastomer. Then I'll give you more details on EPISAFE rubber. Then we will concentrate on few workflows which can be run within EPISAFE rubber. This is a typical process flow involving in this, the design engineer will design the CAD model and passes that to the FEA engineer. The FEA analyst then runs the abacus model, then calculates the nominal stresses and strains. Then this particular rubber model will be taken into EPISAFE. EPISAFE then takes these stresses and strains and creates a sequence of solutions. These sequence of solutions are used to create loading history to predict the fatigue of a rubber component. Material available from EPISAFE Endurica database or from the test, we have a flexibility of using both. These two can be used to predict the fatigue life of rubber component. This fatigue life of rubber can be viewed using as a contour plot in your FEA viewer. You can see here all the supported input and output formats that EPISAFE can interface to. EPISAFE rubber is an add-on module or a plug-in interface to EPISAFE standard modules. I will start with an introduction to Endurica LLC, which is a company with which Dassault Systèmes is partnered to produce the technology behind EPISAFE rubber. Endurica is a company based in Ohio, USA, which is a company which is completely 100% focused on elastomers and elastomer durability. They have a 100% license renewal rate and has a good acceptance on market space. Customers are there in number of sectors and are continuing to develop workflow in diverse industries. Durability solution for rubber. So in developing a rubber component, there are a number of challenges the company need to meet. You have to know how your material behaves with regard to fatigue. And also, you need to be strategic on how you use your test labs. Often the capital spent by the company on the expensive testing machines are very high. So we want to be strategic in qualifying the correct design. Also, you have to know how to use this simulation process to minimize the design risk. It's very common for company who develop rubber product to spend lakhs of rupees on mainly testing. So before the testing phase, you need to be confident on your design. So one way to do that is by using simulations, which allows us to model and validate our model or our design, and FEA and EPISAFE rubber can be a good option. This slide is an overview of EPISAFE rubber, which gives you a user-friendly GUI, and you can access various functions from mainly Endurica Fatigue Solver. You can use it. It also manages to provide the results of FEA analysis. It interfaces very nicely with abacus. It contains a material database which currently has a database of around 25 rubber materials. You can use these materials for your analysis, and many customers use their own tested material for the analysis, which can also be saved in the FSAF material database locally. And software comes with a good tutorial and user manual also. In the bottom, you can see the software package, which is a complete solution, I would put it in that way. We provide training classes on focused mainly on this is the FSAF rubber, and also how to measure fatigue behavior of rubber materials, and also on the analysis aspects, which we demonstrate on how to take your model and use that for predicting fatigue life. Endurica is also into services where the customer can send their rubber material and have them characterized. Support will be provided to you locally, and also large experimental program have been run to validate various different pieces of calculation and published in literature. Here is the high-level workflow. You will start with your preprocessor environment, where you create your mesh, and then you create and apply loads and boundary condition. And loads may be forces or displacement. And you use your FEA solver to define the typical scenario of loading over time. Okay. And it can be a simple option, or a simple sine wave, you can do it, or you can also use complicated road load data. So you will build up your loading history and then run it like in time domain solution using FE code, which will produce your output file. This one will have stress tensor as well as nominal strains at each time point in each in time domain, and each elements. This database is opened and accessed in FSAF, where it is used to define loading definitions, and also material property will be assigned here only. FSAF is interfaced with Endurica solver to compute fatigue life. In addition, the fatigue life, Endurica can also solve few other things, which will end up in Endurica auxiliary files. First, let us understand what this life in FE database is. After completion of the analysis, FSAF will write the result file in another ODB file, which will have the fatigue life of whole model for all the elements. This is the number of repeats of loading history as given in the loading of FSAF user interface. Whatever you initially define, that many number of repeats of life will be shown as a contour plot. And also, excuse me, Endurica fatigue calculation are based on crack propagation. So life is a number of these repeats of loading needed to grow this crack from an initial specified size of the crack. So this is one of the output FSAF rubber gives. Now let us understand these auxiliary files. These are some intermediate variables which are calculated during the FSAF rubber analysis process. This can be used to provide information related to fatigue failure of the process. For example, if you want to know what is the history of damage parameter is due to the defined loading or at a critical location, you will get it in Endurica auxiliary files. Also, information related to rainflow counting on critical plane. These can also can be an output in FSAF Rubber. Also, there is a output called damage sphere, which gives the direction of the largest damage at the critical location. These are the things which will help you understand your component or damage process better. Problem statement. This is a typical problem statement for rubber fatigue analysis. On the left-hand side, you can see a topic taking the material properties which indicate the stress strain curve, and also we have we can take the definition of fatigue crack growth law. Also, as part of the material property, the size of the crack precursor that already exists in the material can also be taken. On the right hand side, the strain history can be brought in, which we calculated or which is available from the output database file. From the these things will be brought together to predict the fatigue life of rubber. Now let us understand few typical problems. Material. There are several typical problems that companies face, and companies can use FSAF rubber to overcome these problems. First typical problem is material sphere. Rubber is a highly customizable type of material. This means that typically you can change the material property, and there is a change in fatigue life also. So using FSAF rubber, various effect of these material property on the fatigue behavior can be easily studied. Next comes technology. Let us understand the technology which is behind this FSAF rubber. This is a list of material model which is used in FSAF rubber for better understanding on the behavior of the material. For the stress strain loss, there are mainly 6 different material models available. These are called a strain energy potential function, and any one of them you can use for your fatigue analysis. For defining fatigue behavior, you have to define your crack growth rate law, and crack precursor size also you need to define. We also provide material model which are used for strain crystallization or amorphous material which do not crystallize. Using these material models, temperature dependence of material can also be studied. Even time or environmental dependent factor can also be included. Even there is a lookup table which is available for strain crystallization method, which will let you do very accurate crystallization effect can be accommodated in the analysis. Characterization. Earlier I mentioned that FSAF is having a database of material, and also FSAF can include tested material model also. So Endurica offers services in various testing aspects of this material modeling. So it mainly focuses on 4 different testing areas, and even estimation of crack, precursor size, and other cases depending on scenario. They help us in the testing. Here is a validation case for strain crystallization. Endurica has integrated nearly 60 years of research from various literature and validated this safe rubber. This slide you can see, this shows mainly strain crystallization effect for natural rubber. These are fatigue crack growth rate curves that are plotted for different R ratios. That is nothing but which is load is fully relaxing or non-relaxing. You will come to know from R ratio. You can see that at R is equal to 0, there is a fastest rate of crack growth, and if R increases, the rate drop off. You can see that, and you can also see that there is a good correlation between the literature results to that of efficient rubber. Efficient rubber simulation results are in green color, whereas literature results are also highlighted. Here is a case study of silicon knuckle joint. In the medical industry, mainly in US, these type of device should survive for more than 100 million flexible cycles. So 2 rubber materials can be compared, and we can find out which is better durability design. Another typical problem industry faces is geometry. Let us understand this geometry. So we need to understand, for better understanding of this design, both stresses and stress concentration regions should be avoided. And FSF can help you in identifying these minute details, like stress concentration near holes or cutout area can be identified easily, and you can do your optimization. Technology behind this is critical plane analysis. This is a key technology implemented by Endurica. We have stress and strain tensors available from the result database. These quantities will be resolved onto a specific plane as a function of time, and this can be used to evaluate the damage. We do the rainflow counting and use crack growth rate loss will be used to calculate the fatigue in a particular direction. This will be repeated at almost all the orientation to calculate the most damaging plane where the crack will initiate. And this accounts us to consider that this is a very good approach for identifying the crack. Here is one more validation case of multi-axial loading. A validation case for this is a 4-year research program by Dr. Wilmas, who is behind FSF rubber coding. Here the number of components were tested in tension and tension plus shear, compression plus shear, and both designs were All these cases were studied, and also proportional and non-proportional loading also studied. And you can see there is a good correlation between observed and simulated result. It also allows us to predict the orientation of the crack plane. On the right hand side, you can see the crack generated or crack propagated, you can see there. And the lines mentioned in colored lines, mainly red and green colored lines are there. These are the predicted orientation by the software. And you can see there is a very good correlation between orientation predicted by software as well as experimental results. Here is one more case study. This is mainly on exhaust mount. This particular case study has been done by Endurica with 4 other partners or 4 other customers, and one of the customer was Land Rover. And here mainly the this case study is mainly for geometry analysis. And Endurica fatigue solver was able to predict the failure at nearly 3 out of 4 cases very accurately, and there is a very good correlation between testing and simulation. Another typical problem comes is loading history. So this is a final typical problem which we are discussing here. General problem related to loading will be there will be a bigger static load, which may be weight of an engine or weight of a vehicle, and followed by coupled small dynamic load on top of it. So, and another example would be a preload on the bushing isolation, or where there will be kind of swagging type of effect. So these type of effect can be easily simulated using FCF rubber, and key technology here is nothing but rainflow counting for damage accumulation calculation. This technology enables you to take the complex loading as shown in the figure there, and we have a crack driving force at various location, or at a location of our interest, which is mainly energy release rate for one typical cycle, one cycle of repeat, we can say. So we use the rainflow counting to identify the individual cycles in that loading history, and then we calculate the crack growth rate. So here is one more validation case. Here mainly damage accumulation under variable amplitude loading is studied. And this is another experimental program which is done in University of Toledo. This again proves that under variable amplitude loading, fatigue calculation works fine in FSAF rubber. Here the researcher took various variable amplitude loading histories, and also he has taken various materials also, and the mainly loading includes cycle which is means varied amplitude and varied mean, and a different combination of loading also considered, like axial or torsion, and a combination of the two. And you can see that from the plots, it is seen that experiment is done in two different materials, mainly filled non-natural rubber and filled SBR type of material. And efficient rubber is again in good correlation with the lab results. Here I have a bushing example which is under road loading. This is a bonded bushing example which is under two channel loading, mainly one is in vertical direction and another in horizontal direction. These forces are applied at the inside location of this particular bushing. So after the analysis, you can see the results results are plotted only at the surface and is highlighted in a red color, and you can see that the crack is generated around 3 lakh cycles. And apart from this, we can also predict which are the most damaging loading out of the two. We have two different loading. If we say if rubber will predict which is the worst load among the two, which is causing more damage to the bushing, that can also be studied. So I have one demo problem. This is a rubber plate problem. You can see in the figure right hand side, this is the plate which is under fixing in the bottom and loaded from the top, and loading is given by variable amplitude type of loading as seen in the left hand side. So 0 to 1 second, it has nearly 5 different increments. So how to do this type of problem in FESafe rubber, we will see. I'm launching my abacus. Yeah, this is the rubber plate which I was talking, and from the bottom it was fixed, and from top it was loaded, and mainly we will concentrate on material model. Here rubber material is used, C10, C01 and D1. These are mainly three coefficients of polynomial type of strain energy potential. Same material will always also be used in FESafe to predict fatigue analysis. We will see how we have done this FE analysis. Here you can see the FE results. You can see the deflection and in this rubber plate. the component is loaded mainly in this fashion. So in the beginning it is 0, and also in the end also is 0 deflection, whereas there is a peak loading coming here. So let us consider this FE results for our fatigue analysis. I'm closing this window and I'm launching FE Safe. As I told you earlier, FE Safe Rubber is a plugin to FE Safe standard. I'm launching this particular demo problem. For the benefit of those who did not attend yesterday's webinar, FE Safe will have mainly 5 windows where you connect your model with your material database as well as with your available loading files. So this is your material database window. This is the current FE model window. This is a loaded data file window. And these are the 3 places where we input our 3 key inputs. And you can see it here. This is a fatigue from FEA window where we connect these 3 key inputs with the model. I'm clearing this here. I'm opening finite element model. Here is my ODB file or result file. I'm pre-scanning this to check the available output. We should always keep in mind that for rubber fatigue, we should always request strain. And since rubber is not a linear material, we have to consider both stresses as well as strain here. And also it is even in between results are also important. If it is a linear analysis, we could have given last increment only, but since it is a nonlinear analysis, even intermediate solution is also important. So I'll unmark this and I'll select all the results. I'm selecting my units. I'm pre-scanning this. I have only one data set, material 1. Here you can see now FE model is loaded. Both stress data set as well as strain data set at various increments, starting from increment 0 to increment 5. You can see it here. So we have a result for individual points here. We need to consider this as one cycle. I mean, we want to predict the fatigue life of this rubber component. How many such cycles it will withstand is my area of interest now. So what I have to do is I have to sequence these increments, and because of that I don't want any I need not load any data files here, since I'm going to sequence my data set. So after completion of this, my load starts again from this. So this is one cycle, and how many such cycles my component will withstand. Let us check it. I'll go to loading setting window here. I'll clear all the loading. I will click on this stress data set. I cannot add this like this. So what I will do is I will create a loading block, and then I will add a data set. Okay. So since it is a nonlinear analysis, we only stress results are not enough. So I need to connect the stresses with the corresponding strain. That I am adding it here. So now my stress and strain are interconnected. For sequencing type of analysis, what I need to do is I can write it something like my last data set 1 to 11, 1 to 11, inside the bracket at a gap of 2 increments. So this is nothing but it will select stress data set 1, 3, 5, 7, 9 and 11 at a gap of 2. You can see it here 1, 3, 5, all these even number data set are related to stress data sets. Now I'm connecting strain data sets. Again I'll write 2 to 12 inside bracket at a gap of 2. So my data sets are sequenced now. So 1 to 11, 2 to 12. After completion of this one cycle, it will go back and again it will consider, it will come back from 1 to 11, 2 to 12. Coming back here, I will click on do not analyze here on this default group. Let me leave these subgroup and surface finish as it is. I have to define my rubber material. I have copied this Endurica material into Endurica material database copy. Since I need to edit this for demo purpose, I have edited this value. I have taken here reduced polynomial type of strain energy potential, and the corresponding values I need to put. For reduced polynomial, I need to put C10 as 1, C20 as 0.1, and I will mention D1, which is 0.00067. These values we have seen. These are the values which is used in our FE analysis. So I have renamed this as demo inside Endurica material copy. I will select this and I'll go back here and I'll double click on this and define the symbol. So material 1 will be assigned material property of demo. Now I need to call on this FSF rubber plugin. For that I'll give load plugins. Endurica plugin is available here. I'll click on OK. My plugin Endurica is loaded here. And also Endurica LLC or FSF rubber is having a algorithm called Endurica. This particular Endurica algorithm will be selected automatically if we select analyze using plugin algorithm. Here we have three different options. I will go for surface since I have used my shell element. We need to use bulk and bulk with pressure for solid type of elements. I'll give OK. It has taken Endurica algorithm or Endurica surface algorithm. Here my job is done. I will give analyze. So FSF is calculating the life now. It will take a minute. Analysis is completed nearly 31%. Yeah. FSAF is predicting a life of 64,000 cycle for that type of loading, and it is also mentioning the element number. Now I'll go and check my results. Launching my Abacus CA. So I can, I'm plotting it here. And the worst life observed is in these locations. So we can also see out of these which element is having worst life. Is maximum. Now let us see what happens if I remove these elements. These are the elements where there is very less light. Removing this. So FSX will predict the next burst life. If I remove this again, so you can see now I'm putting all the elements. FSAF will predict the next worst life if we remove a particular element. Let us say that this is my worst element, or the element which is having the worst life. I will remove that. Sorry, I have to remove this. So FSAF will predict the next worst. You can see it here. So like that, only you can change to check various fatigue failure locations, or also if you want to check at a particular location, whatever is, you can say that this is my critical location. Here also you can check your fatigue life. At individual node, fatigue life can be seen. So this is a brief demo on FSAF rubber fatigue of this elastomer components. So let us summarize today's webinar. So mainly, first of all, rubber fatigue in a different type of analysis we have done. Mainly, I would say that rubber fatigue is completely different than this metal fatigue. So mainly because of a special behavior of rubber. And we understood mainly how FSAF can be used to solve various problems related to material or geometry or loading issues. This way you can make better decision on your design and accurately build your material behavior, and also for various service environment. So I would like to conclude that for better design, we can use FSAF rubber to predict fatigue of elastomeric components. Now we are open for a few question and answer sessions.